So before we talk about power series, let's review this. What kind of series is that? Good. You should recognize that's geometric. And so I want you to, when you see that, right, see this notation right here, you think what? Write it out. Right? Write it out. What does this mean, or what do you think when you see that? Go. I'm going to call on somebody in a second. See that? Think what? What does it mean? Write it out. Dylan, you're up.
That's going to be A plus AR plus AR squared plus AR cubed.
So he said A plus AR to the first plus AR squared plus AR cubed. What do you think? Yep. Okay, so what we want to do is, so everything we've done so far, or most of what we've done so far, we started with I equals 1, and that went back to sequences. Why did we start with I equals 1? It was kind of the most natural thing to do. Why did we start with I equals 1 and then go 1, 2, 3, 4? Just a very natural choice when you're thinking about sequences. Why is that? Why do we choose that? Yes, sir?
Is it because, like, if you have I equals 0, then the output will be 0, and you can kind of ignore that? It can be 0.
Maybe not. It doesn't have to be 0. Why do we start with I equals 1? Yeah?
So that I matches like the number, the value I got right now.
Right. So that the I is telling you which term it is. Right? So if I equals 1 is the first term, and then I equals 2 is the second in the list. I equals 3 is the third in the list. So that's just a totally natural way to do this. But you can start like a sequence or a series, especially a series. You can start it, you don't have to start it at I equals 1. Okay? So we did that with sequences, and we've done that with series just because it was a natural choice. But it can start at, say, 0. Lots of these series you'll see in the homework and the test, they start at I equals 0. Okay, so I want to write this exact same geometric series. I want to get the same exact terms added together, starting from I equals 0 now. So how would I have to change the formula? So everyone think about it. How would I have to change the formula so that when I start at I equals 0 and start marching up, I'm going to get the exact same terms. So write it down, see if you can think of it, and write down the new formula that's going to generate the exact same series starting from I equals 0. Where's Cameron? Cameron Baca. Is Cameron here? How about Damien? Is Damien here? Yep. Did you come up with the formula? He wants A times R to the I. Yep, I see some nods. Right, and so A times R to the I is the exact same series. Why? Because it generates the exact same terms. Now when I is 0, you get A. When I is 1, you get AR, etc. Okay, so this is called, this technique, generating the exact same series with a different starting value, is called shifting the index. Shifting the index. And notice, what do we do to the index? We shifted the index back, right? We shifted it back by 1. And then how did that change the formula? Then what do we have to do to the formula? What do we have to do to the exponent of r? When we shifted the index back by 1, then we have to add 1 to balance it out, right? So that we get, so our first exponent is still 0, right? So if we move all the indexes back by 1, then we've got to increase in the formula, we got to increase them all by 1 so that we get the same terms. And then this kind of way of doing a geometric series is a little bit cleaner, right? So it's nicer to have the exponent be I minus 1 or versus I minus 1. So this is kind of a more kind of compact and kind of cleaner way to write a geometric series. So from here on out, these are both the same thing. So be familiar with both. So we can start a geometric series from 0, and then that makes the exponent just I. Okay, so that being said, now we can talk about power series. So power series has this form right here. So You see that? You think what? Write it down. You see that? You think what? Everyone write it down. What does that mean? Where's Eric Pierce? Is Eric here?
Yeah.
Where's Eric?
I was writing it down.
Okay. Can you? Any idea? Can you tell me? All right, so what do? We start with I equals 0, and that gives us the first term. So what do you get when I equals 0? Right, c of 0, x to the 0. And then what do? C sub 1. And what am I doing with these now?
You're adding them.
Adding them, right? Next one?
C to the second, and then x to the power of 2.
Right.
And then just goes on.
Goes on and on and on. Yep, so this, what does this notation mean? It means add up a bunch of things, right? It's a series, it's a sum. What do we add up? That's the formula that tells us what every one of them are like, right? Start with I equals 0, then I equals 1, then I equals 2, and add them all up. What does it look like? The power series, what does it kind of look like? Looks like geometric. Okay, but there's a couple of differences here. So there's two key differences. What's one of the key differences between this and, yeah, Neil? Right, before, look, and the a's are all the same, right? So here they have the same coefficient. Now you have a coefficient that depends on what I is, and so it can change, right? So it's like its own sequence. Like you have a sequence of coefficients. That's the first difference, and then the other difference is even more significant. What's the other difference here? Just visually, what do you see that's different without? It's x instead of r, right? So x instead of r. So r was a constant. And when we think of x, what do we think of x? Variable, right? Variable. And that's what it is. Okay, so we've got our real valued coefficients that depend on I. They change, right? They change. It's its own sequence of coefficients. And then x is an independent variable. So now this hopefully looks familiar. A coefficient times, so this is like a constant, then a coefficient times x to the first, plus a coefficient times x squared, plus a coefficient times x cubed. We know what that is, right, from our mathematical past. What is that thing? Polynomial, right? But there's something very different about this polynomial. What's different about this polynomial from any other one you've seen? Goes on and on and on, right? So yeah, so this basically what a power series is, it's like a polynomial function, but with an unlimited number of terms. So you can think of this as like a polynomial, like a function. But it's like, it's infinite, right? It's an infinite polynomial. So that's what power series are. They're like polynomials with an infinite number of terms. So then, what's the key critical question we want to ask about a power series then? The same key critical question we've asked about every series. Okay, so now, convergence, right? So, but now instead of does it converge or not, we don't have a yes or no question anymore. It's kind of framed differently. So what would our question be now? Yeah. Right, so if x is a variable, x can change, then we're saying for what values of x does it converge and the rest it doesn't converge. So that's how this is different. So before it was either like yes or no, right? Yes or no, it converges or not. But if x can vary, then maybe there's some values of x that make it converge and others that don't. Okay, so that's, yes sir?
Would you say that this quote-unquote polynomial has an infinite degree?
Yeah, kind of, yeah. That's right. Because, yeah, you just keep adding terms. Yeah, because it's, our index is increasing without bound, and our index is the variable. So yes, it's like a polynomial with an infinite degree. That's right. Okay, so let's look at the first example here. And remember we said that they're very much like geometric series. So we want to analyze them in light of it being a geometric series. And which of our tests kind of tested to see if it was like a geometric series? Last class, right? Ratio test, right? That was the whole point of the ratio test, was to see if it's like becoming a geometric series. And that's exactly, you know, when we look at this, it looks okay. It looks like a geometric series, right? So we're going to use the ratio test. So I want you to use the ratio test to find the values of x which the series converges. So I want you to do the first step, and you're just going to leave x as it is. Just leave x, x, and do everything else the same in setting up the first part. And what was that again? So to do the ratio test, we look at what the ratio of the I plus first term to the ith term. Okay, you can use I or J, doesn't matter. It's just a symbol that means the index. So whether you use I or J, it doesn't matter. But here's, you can check and see if you did what I did. See if this is what you got. And then remember, we kind of combine, we look at things in groups, right? Like things. So we got some x's on the top and some x's on, come back. So we got some x's on the top, some x's on the bottom. So how do we resolve those? What do we end up with? One more x in the top, right? This has one more x in the top than the bottom. So we're going to have an x in the top. And then we're going to gather the other, the rational function together there, 3/4 or 3/4 I minus 1, 3/4 I minus 1/4. And so we're ready to talk about what happens when I gets large, right? So when I gets large, what happens to this right here? What does that become? Should be thinking 1, right? That's a rational function with degrees, equal degrees. So you take the ratio of the coefficients. And then what happens to x when I gets big? It doesn't care what I does, right? It's its own thing. X is its own thing. I can be I, x can be x. I can do whatever it wants, x stays x. Therefore, the limit is not x, but absolute value of x. So when I gets large, that fraction goes to 1, and we're left with the x. All right, so now what does the ratio test say about convergence, right? So this is like kind of like the R value, right? In this case, the R value is the multiplier, and what has to be true about that R value? Less than 1, right? The ratio test is based on geometric series, basically, based on if your series is becoming geometric. So this is like the R value has to be less than 1, and when we solve that, our x is -1 to 1. So what is it saying? It's saying if x is between -1 and 1, then our series will converge. But if it's outside of that, greater than 1, less than -1, it will diverge. Okay, what about if x were -1? What would we get in the ratio test if x were -1? You'd get 1, and what about if x were 1? You'd also get 1, and what does the ratio test tell us then? Nothing, right? So we've got this situation. We know that outside of this interval, the series is going to diverge, but at the endpoints, at -1 and 1, we get this, the limit is 1, and so and the ratio test can't tell us. So what do? Yeah, we're going to find those particular series, right? So take x equals -1 and find the series that you get. It's no longer a power series. It's just like all the series we've done before. So what series do you get when x is -1? So you go back to this. So what series do you get when x is -1? Can you write it out? Write it out. What series do you get when x equals -1? You get this. You get -1 to the j over that denominator. So now we've got one of our previous problems, right? We've got to reach into the toolbox and start chiseling away at this and figuring out if it diverges or converges. So first question, does that approach 0, right? Does that go to 0? If it doesn't go to 0, then we're done, right? It diverges. So does that sequence go to 0? Certainly, right? The denominator gets big. Nothing else, and this alternates, but that's denominator. So it goes to 0. So what can we do? We got an alternating sequence that goes to 0. Can we conclude anything? What do you think? Can we make a conclusion? The sequence goes to 0 and it alternates. Converges by alternating. That's exactly what the alternating series test says. If the positive parts of the terms go to 0 and it alternates, then your series converges, right? So we just added another value of x for which this thing converges, -1. Okay, so what about x equals 1? What series do we get then? X equals 1, then the numerator just becomes 1, right? 1 to any power is just 1. So now we get 1 over the denominator. And now we again look at this one. Does this converge or diverge? 1 over 3/4 j minus 1. Okay, so this is no longer alternating, so we need something else. So we ask, is it geometric? Is it p-series? Can we compare it to something? Those are our tools, right? So, right, this is really similar to harmonic series. So how does it compare to, how do those terms compare to 1 over j? Because the same power, right? So all of these fractions are bigger because 3/4 makes the denominator smaller, -1 makes the denominator smaller. So all of these terms are bigger than the terms of 1 over j. And the sum of 1 over j does what? That's the harmonic series. We proved, we showed it diverges, so therefore this one diverges. So is that direct comparison or limit comparison? That's direct comparison. So that's diverges by comparison to 1 over j. So now we know exactly which values of x it will converge for and which it will diverge. We know it will converge at -1 and then everything up to 1, but then not including 1. Because we had to test those endpoints separately. Why? Why did it do that? Okay. Oh, because I was in the wrong thing. There we go. Okay, so we can graph that. Let's graph that solution. That's on the number line. So here's the values of x for which it converges. Include -1, and then everything up between, and then not include 1. So what's the center? So this is called the interval of convergence. Interval. Interval gives you all the x values for which it converges. What's the center of the interval? 0 is the center. And then you go out equally from the center to show kind of what the width is. So that's kind of like, you think of the center being 0, and then you kind of have like 2 equal wings on either side. It's kind of like a circle. Around 0. And what's the radius of that circle? 1. All right, so our radius of convergence is called, that's what this is called, the radius of convergence is r equals 1. So the radius just gives you some idea of like the size of the interval of x for which you have the series convergence. So how does the radius compare to the whole width of the interval? Here's the whole width. The whole width is 2, right? From -1 to 1. So we've got an interval that's 2 wide. How's the radius compared to that? Half, right? So the radius is half the width of the whole interval. Does that make sense? Okay, so now I want to go back and look at this example a little bit more. So questions on this. So it converges when x is between -1 and 1, and then including the left endpoint, but not including the right endpoint. And that gives us a radius and convergence of 1. All right, so I want to go back here, and I want to look at the original. All right, and so before we even could have talked about this, or before you came into class today, we should have been able to write, what does this mean, right? See this, think what? Practice again. See this, think what? I'm going to call on somebody, okay? So you see that, you think what? Write it down. What does it mean? Okay. Okay. Okay, so is that 1.5? Okay. And on and on and on. So let's simplify that. So this is -1. And then what is that? That's -1/4, right? Which means -4x. Okay. This is 1/2, so plus 2x squared. I think that's what, 5/4. So 4/5. Is that what you got? Okay, so again, what are power series? In essence, power series are what? You're looking at it. Infinite polynomials, right? Infinite polynomials. So then, what would the partial sums be? So I want you to write down the partial sums. So now j starts at 0, so I want the partials, the 0th partial sum, the first partial sum, the second partial sum, and the third partial sum. So write down the partial sums. And by writing out the series, what it means, that makes these partial sums, you can just write them down pretty quick. Where's Christopher Langendorfer? Christopher here? Nope. Where's Odetta? Is Odetta here? Odetta Lou? Yeah. Did you get the first partial sum? So remember what partial sums were? It's where we, instead of having the whole sum, then we just take little parts of the sum. So what's the first partial sum? So like we keep gathering more and more terms. So the first one we'd have, like when for 0, -1, right? And then what would the next partial sum be? You have -1, and then also partial sum is where you keep taking one more each time, right? What's the next one? Negative 1 minus 4x. 2x squared, right? Then so what are the partial sums then? So if you got a power series, what are the partial sums? They're not like polynomials, they are polynomials, right? So these are true polynomials, right? Finite number of terms with some, x coefficients and x to a power, right? And what did we say about partial sums? How do they relate to the actual series? How do the partial sums relate to the actual series? Yeah, they approximate it, right? Which one of these approximates it's the best? The third one, right? The higher order partial sum approximated better. And then if we make a list, we take the sequence of the partial sums, and where are we heading in that list? To the series, right? So if we keep making the list of partial sums, we get a better and better partial sum each time because we add one more term each time. And then the limit of that, where we head to, is, should make sense, the whole sum, right? Because you're making a list where the next one in the list has one more term each time. So if you just take that to the end, you get the actual sum. Okay, so let's take a look at what happens here. And where did this converge again? Between? Negative 1 and 1, including negative 1, not including 1, right? So I'm going to graph the partial sum. So what was the first partial sum again? For j equals 0? Negative 1. So what does that look like? Doesn't look like that. Okay, what does that look like? Negative 1. That's a function, right? And there's that function. It's just x or y equals negative 1. All right, next partial sum. Oops. Negative 1 minus 4x. That's a linear function, right? So there's the second partial sum. Or for j equals 1, p equals 1. Here's the quadratic partial sum. 1 minus 4x plus 2x squared. So what's happening? So why did I highlight part of it blue? Yeah, so what's going to happen is I keep taking higher and higher partial sums. What's going to happen to this graph? It's going to, what's the word? Converge, meaning this graph is going to, as a whole function, within those bounds for negative 1 to 1, it's going to approach some function. It's going to get closer and closer to some function. But then outside of that, it's not going to. It's going to blow up or do something different. So let's watch it happen. So this was the quadratic. Here's the cubic partial sum. Here's the fourth power partial sum, and fifth, sixth. So notice that the blue part is kind of honing in and it's getting more and more still, right? It's converging upon a particular function. But outside of that, like on the left, it keeps flipping, right? It keeps flipping negative, positive, infinity. And on the right, it's just heading out to positive infinity. So here's the 20th degree polynomial. And for the last several, that between negative 1 and 1, it just didn't move, right? So because this function is converging in on a particular function. So let's make it really big, say 401 or something. So now this is the partial sum that has to the 401st power. So as soon as you get past negative 1, it just crashes to negative infinity. As soon as you get to the right of 1, it explodes to positive infinity. But in our interval of convergence, it's what? It has kind of converged in on a very specific function. That looks a lot like what it was when it was, p equals 4. Or say 10. So look at it at 10, look at it at 400. That's really big. Yeah. Okay. So that's getting to the idea behind these power series, right? in the interval of convergence, as you look at the sum, it's going to converge on a particular function. But then outside of the interval of convergence, blows up. Okay, that's way better than you think. Okay, here we go. Next one. Already did all that, so let's try this one. So we're going to ask for what values of, thank you, for what values of x does this converge? We're going to use the ratio test to do that, right? Use the ratio test to figure out for what values of x will this power series converge. Okay, check and see if you agree with the first step here. Except for the, this would be -1 to the I. There's an n there. There's n to the I. Agree with that? So now we're going to gather our x's together and our factorials together. So when we gather our x's together, what's the overall result of the x's, top and bottom? What do we have? Where do we have more and how many more, right? Where do we have more and how many more? 2 more on top you should get. You should have gotten 2i plus 3 versus 2i plus 1. So that means there's 2 more x's multiplied together on the top than on the bottom. So that would give us x squared. And then let's write out what, so, and then this is, what factorial is this? 2i plus 3, 2i plus 3. And let's just practice. Let's write out what 2i plus 3 factorial is for practice here. So 2i plus 3 factorial. What is that? Nick?
It would be 2i plus 3 times the quantity of 2i plus 2 times the quantity of 2i plus 1 factorial.
So 2i plus 1, then what's next? 2i, and then? And we keep going on and on and on like this until we reach?
Times 3 times 2.
Yeah, could I put a 4 here? Does it have to be 3 times 2 times 1? There is a 4 there, right? Is there a 5 there?
Yeah.
Yeah. Is there a 6 there? Yeah. Okay. So there's nothing magic about 3 times 2 times 1. Sometimes we write that. So, but just so you know, there's also a 4 and a 5 and a 6 and every number up to 2i minus 1, 2i, etc. So then, what do we have? What factorial do we have in the top? 2i plus 1 factorial, which is part of this, right? Like he said, that is 2i plus 1 factorial. Leaving what? So all those, starting at 2i plus 1, all those factors cancel out, leaving what? Just these two are left in the denominator. Everything else cancels out, and we're left with just that, right? And now we're ready to take the limit, which means let I get really big and see what happens, right? So when I gets really big, what happens here? What does that become? 0, right? It's got a big denominator, -1 over a huge denominator, 0. And what happens to x squared when I gets big? X squared, so u be u, I. I'll be x squared. And then, so then what happens in the limit? What's the limit? The limit is 0 times anything is 0, right? So if that fraction goes to 0, it doesn't matter what x squared is. The limit is 0. And according to the ratio test, when does this converge? When? The limit is, what does the limit have to be to converge? Less than 1. So the question is, we're asking what values of x makes the limit less than 1? What values of x makes the limit less than 1? What do we get? We got the limit was 0 for all values of x, right? So for what values of x is it less than 1? All values of x. No matter what x is, this thing goes to 0, and so it's less than 1. So what's our interval of convergence? All real numbers. And what's the radius of convergence? So the radius then is like a value. So the interval is an interval, so all real numbers, say negative infinity to infinity. So what's the radius of that? Half of infinity, right? Well, that's just infinity, okay? So all real numbers means negative infinity to infinity, and then we have an infinite radius. Questions on this example? So what it's saying is, for all x values, if we were to graph the partial sums and start looking at the higher and higher order partial sums, it would converge for every x, right? It would converge onto something for every x. And we'll find out later that this is actually what converges on. This is cosine, I think. Is this sine or cosine? Oh, is it sine? And we'll find that out next week. Stay tuned. This is actually converges to sine for all real numbers. Mind blown. Okay. All right, here we go. Easier example. Here we go. Where's Hannah? Is Hannah here? How'd it go? So do you agree with my first step? Okay. How about Elizabeth? Is Elizabeth here? March? Okay, so then can you, what about the x's? What happens with the x's, Elizabeth?
It would go to
Just x, good. And what about the 2's?
the twos. What is that just is 2 also.
Where?
On the bottom.
2 on the bottom. And then we'll gather my j and my j plus 1 together. And what else do I have?
And then the negative 1 to the j plus 1 goes to just -1.
Yeah, so I think we get this. Okay, limit is, so j is going to get big. If you had i's, it's the exact same thing, right? It's just a different symbol. It means the exact same thing. So you could use i's, j's, whatever. Okay, limit of this. So 1/2. X halves, right? X halves. So this should really say this goes to x halves as j gets big. So we got to figure out for what values of, well, we want to know for what values of x this converges. So for what values of x will it converge? When that is x over 2 has to be less than 1, right? Like a geometric series. That's kind of like the R of a geometric series. So that means x over 2 is going to be less than 1 and remember solving absolute value inequalities. If x over 2 is less than 1, that means x over 2 has to be between -1 and 1, which means x has to be 2 to -2. What about at 2 and -2? So if you put in, so if x is -2, you actually get the harmonic series. You can prove that later. So therefore, converge or diverge? Diverges. When x equals 2, you get the alternating harmonic series. Figure that out later. Work on that later. And what about that? Converge. Therefore, what's the whole width of the interval? What's the whole width of the interval? 4. Radius of convergence? 2. Okay, will it always be one side will converge and the other sides won't? No. Sometimes both sides converge, sometimes neither side converges. So there's no pattern to that. You got to always try them both. Always try them both.